All right. So it looks like we are live now for the Google Hangout. This is the Equilibrium Hangout for AP Chem. Our unit test is in a couple days. So we'll go over we will go over equilibrium K, calculated concentration, KSP, molar solubility. I'll try to get some other stuff. Oh, the Chatelier's principle. Hopefully somebody asked a question about that. I didn't pre-populate that question into our Q&A app. So as we go along, I might ask somebody to type in that question if they don't already do it. I know that you guys have your worksheets and you have practice tests. And I would like to give some examples, not necessarily from a practice test, so that so it's something you haven't seen before. And then, of course, that idea just occurred to me just as I was starting this. So I'm going to give it just 1 second while you guys are joining. And then in a moment, I'm just going to go ahead and start reviewing anyhow. Sunday night, there may not be a lot of people here. Hopefully there are, but I totally understand if you're waiting until Monday night to do the review to watch this. So I'm going to do a quick search for some equilibrium worksheets for AP Chemistry. And then we'll see what I can come up with and use those as my examples. All right. I will have to say, for some reason, lately my internet has been moving a little bit slower. So stuff has not been coming up as quickly as I had hoped. It is what it is, though. All right. All right. So I think I'm getting some good stuff here. I have something that I can be calculating, or we can be calculating K. We can be calculating. Looks like they're mostly just K. Is there any for concentration? I will see. Doesn't look like it. That's okay. I might have. Maybe Adrian has some stuff. Looks like he might. The only problem is it's the same things you already have. So I didn't know if he had a new. We'll do what we can. We'll see. Maybe I'll modify some of the stuff. So it looks like we've got at least one. All right, Aria. You can always count on Aria. Thank you to provide some good questions. So let's go ahead and get started with his question. Multiple choice number 2 on the practice test. Now, Aria, we had 2 practice tests, and there was one. The first one, I said that one you had to do, and the second one was sort of an optional one that was, you know, it could be more practical, or prepare you for the retake. So I'm going to assume, you don't have to put it in there, but I'm going to assume you mean the first practice test. So I am going to pull that one up. I need to make it a little bit larger. All right. So I'm going to go ahead and share that from my desktop. Okay. So multiple choice number 2 on the practice test, the first practice test, says at a certain temperature, the value of the equilibrium constant K for the reaction, and you have hydrogen plus bromine gases, yields hydrogen bromide gas, and it's an equilibrium, and it has a K that's equal to 2 times 10 to the 5th. That's a very high K. What is the value of K for the reverse reaction at the same temperature? Okay. So this is one of those where you needed to remember, and actually I'm going to go ahead and go and share my Boom Bootable, because this is going to feed into some other questions or some other concepts that I want you guys to be aware of. All right, so let's make it a little bit thinner. There we go. All right. Number 2, multiple choice. Okay, so you had a K that was equal to 2.0 times 10 to the 5th. And the question was, what is reverse K? I'm really writing this sideways. Reverse K. So if you go the opposite direction, going this way, K is equal to 2.0 times 10 to the 5th. Going this way, we have to do 1 over K. So the reverse reaction is always a 1 over K. So 1 over 2.0 times 10 to the 5th. And basically, that comes to 1 over 2 times 1 over 10 to the 5th, which is basically 0.5 times 10 to the negative 5th. It's an inverse, okay? And you have to keep this in scientific notation, which means you're going to end up moving this decimal one thing to the right, so you end up with 5.0. And if you moved it one more over that direction, you then have to take away another 10 from this, so it's 10 to the negative 6th. Okay, now that could be a fake out. It could be 5.0 times 10 to the negative 4th, and that would have been a really good detractor, a really good option that would have distracted you, but there was no 10 to the negative 4th. There was either 10 to the negative 5th or one option that gave you 5.0 times 10 to the negative 6th, and that was B. So that is why the answer is B for number 2. But this is a good time to remember that you've got, so K, if K is equal to, and we'll do that for a lot of these actually. Actually, let me come up with something else. 4 times 10 to the 6th, okay? So if you do, and that's obviously going in the forward reaction. If you go the reverse reaction, that's 1 over K. So that's equal to 1 over 4 times 10, 1 over 10 to the 6th. That's equal to 0.25 times 10 to the negative 6th, which is 2.5 times 10 to the negative 7th. If you end up taking K and you end up, let's say that your reaction was that same thing with the, H2 plus Br2, and you had 2 HBr. And for this one, let's say you did 1/2 H2 plus 1/2 Br2 is in equilibrium with 1 HBr, basically. Oops. Then what you would do is you would take the K and you would square root it. So that's the square root of 4 times 10 to the negative 6th, which is basically just 2, not negative 6, sorry, positive 6, because I said that originally was, let me, 10 to the 6th, which is 2 times 10 to the 3rd. So you square root the number, and then when you square root an exponent, you just divide it by 2. So that means that's, if you, that's another K prime, or K prime prime, however you want to look at it. Like this could be K prime right here, okay? Now, if you're gonna do another one, let's say you do 2H2 plus 2 Br2, and I think you're kind of getting the hang of this, and you know it's gonna happen. 4 HBr, you're gonna take K and you're gonna square it. So then you had 4 times 10 to the 6th, and you square it, and then you've got 16 times 10 to the, remember, you're not squaring that, you're just doubling it. So if you square root, you cut it in half. If you square it, you're just adding them together or multiplying 6 times the 2. So you get 12, which is really 1.6 times 10 to the 13th. So this is K prime, 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 3 primes. And whatever, you know, the prime is a little bit more flexible. You can do whatever you want with that. So those are some things you need to know about on how you would manipulate K. So on the test, I believe I do have a question on you having to manipulate K for a reverse or changing the coefficients or something. So I think it's on there. I can't remember exactly. It might be in the retake. If you end up with a retake, you'll have to know all these things as well. Okay, so that ends Arya's question. So that one's done. We have another question from Ali. Worksheet 13B, Haber process, the whole front page. Fantastic. Okay, so give me a second. What I'm going to need to do is, I didn't go, when I loaded some of the stuff up, I didn't go that far back. And when I say that, what I mean by that is that I did not open up that document. I just opened the most recent stuff because I felt like we covered that already. But if we need to go back to it, I'm okay with that. That's not a problem. Just pull that up for a second. So the Haber process, 13B. All right. And you have the key on there, which is good, but I understand if that wasn't making as much sense. It's actually, what's happening is that you guys are overthinking 13B. Once you see it, you'll understand what I mean. All right. I need to blow it up a little bit so it's a little bit easier to see. All right, let's share that document now that I've done all that work to it. All right. All right, so you can see 13B on the first page. They give you some data. They give you the Haber process. It's 1 mole of nitrogen to every 3 moles of hydrogen gas. They're just giving you the mole ratio, basically. Just a mole ratio. They're not telling you that's exactly how much there is. They're saying that's the ratio. And they're saying that, so it's exposed to those temperatures and the equilibrium is established. Like the equilibrium is there. It's done. Okay? In each case, the total pressure is 10 atmospheres. Now, they're giving you the mole ratio. They're telling you what the total pressure is, and they're telling you what the partial pressures is, what the partial pressures are, sorry. This is not an equilibrium problem. This is a stoichiometry problem. They just want to know how much there is of the other stuff. You're not having to figure out how much there was initially. You're not having to figure out changes. It is. They're tricking you by calling it equilibrium. But it's not an equilibrium problem, okay? I'll do the first one. Once you see it, it's actually pretty easy. You'll be able to understand how to figure out the rest. So 13B, A. Let's do the 355 degrees Celsius. The partial pressure of the, the partial pressure of the NH3 is equal to 0.741, okay? And the equation is N2 plus 3H2 is in equilibrium with 2NH3. And the total pressure, P total, is equal to 10.0 atmospheres, all right? So this is, I guess, I don't know how you know. You need to look at it, but they're not talking about, you know, they're not saying, oh, find the initial concentrations, find the change. Equilibrium is already established, and they're giving you the numbers. So if you remember, P total is equal to the partial pressure of the N2 plus the partial pressure of the H2 plus the partial pressure of the NH3, which means 10.0 is equal to, using the coefficients, x plus 3x, right? Because whatever is left over there, they have to split up, plus 0.741. And oh, these are atmospheres. I guess I should probably put that on there. okay? So you're basically just solving for x, and then that's going to tell you what it is. So you do it 10.0 minus 0.741. I need to keep using the units, sorry about that, equals 4x. And then, let me pull up my calculator, which I should have done at the beginning of the session. I didn't. So if I start plugging that in, let's see, 10 minus 0.741 divided by 4. And that means that x is equal to 2.31 atmospheres, which is equal to the concentration of the N2. And then 3x, so I just take that, multiply times 3, and I get, so 3x equals 6.94 atmospheres, and that's equal to the concentration of the H2. And that should be it. I haven't looked at the answer key. I don't know. Let me see if I can find that real quick, because just to confirm if that's the case. And looking at the answer key, that is the answer. So using that, you can definitely find the rest of A. And then I guess because you asked for the whole sheet, so I guess we'll go ahead and go on to B. I'm sorry, just give me 1 second. I happen to see that Joanne Chung asked a question about 13A, so I'm just opening that up real quick, just so I can have it ready. Okay. So for each temperature, calculate Kp. Okay. So now that we have the values for each of the Ks, and we write up the K value, Kp is equal to the concentration of the NH3, oops, brackets, squared, over the concentration of the N2 times the concentration of the H2 cubed. Now, if it was still X, we would have to do 3 times X in the center right here, but we don't have to do that anymore. This part should not be hard for you, honestly. Let me go back a second. I don't remember what the values were. All right, 0.741. 0.741 squared over the N value, 2.31 squared. Oh, what am I doing? That's not squared. Sorry about that. Times tedious. This is should have done the same way. 6.94 cubed. Okay, that's math. You can do it. I'm not doing that one anymore. Okay, so that's how you solve that one. All right, that was A, that was B. Oh, that was the whole front page. And then you can figure out the rest of it. I think that was the rest of it. You just said front page, right? Haber process, front page. Good. All right, we're done. Right on. All right, so let's move on to our next question. And I told you I saw Joanne. So Joanne's was here, 13A worksheet problem number 1. So let me pull that document up. Whoops, that's not it. Okay. 13A, there we go. That's a little small. Let me make that bigger. 13A, I didn't remember which number. 13A problem 1, perfect. All right. The equilibrium constant for the reaction below at a given temperature is 45.6. Oh, I remember this now. The answer is off. It said like times 10 to the negative 10, and it should have been like, I think that's right. I don't know. Whatever it is, it's off by like a factor of 10. I'll do it. And so the key was wrong, but I'll go ahead and do it anyhow. If the equilibrium concentrations of F2 and BF3 are that, calculate the equilibrium concentration of BR2. So we can do that. So I'm assuming that some of you have that in front of you. You can see it. I am going to switch to my bamboo tablet. Okay. All right, so we're looking at number 1, worksheet 13A. So our equation is Br2 plus 3F2 is in equilibrium with 2 BrF3, and they're all gases. And K is equal to 45.6, and the concentration of F2 is equal to 1.24 times 10 to the negative 1, and the concentration of BrF3, wow, my handwriting is getting worse by the second here, 1.99 times 10 to the negative 1. And so we are looking for the concentration of Br2. So you just set it up. K is equal to the concentration of BrF3, and that one is squared because of its coefficient all over. Concentration of Br2 times the concentration of F2 cubed. So 45.6 is equal to, and we're looking for, okay, so BrF3 was 1.99 times 10 to the negative 1 divided by, we were looking for, I forget, Br2. Yeah, so Br squared, or Br subscript 2, sorry. And then we have the concentration of the BrF3, I'm sorry, the F2 as 1.24 times 10 to the negative 1 cubed. So basically what we come out with is the concentration of Br2 is equal to, we just switch places with the 45.6, 1.99 times 10 to the negative 1 divided by 45.6, and also divided by 1.24 times 10 to the negative 1 cubed. So I'll plug that into my calculator. 1.99 exponent negative 1 divided by 45.6 equals, divided by something went wrong. Sorry. 0.199. Oh, I missed a button. That's what happened. I was like, this number can't be right. And then that number divided by 1.24 exponent negative 1. Oops. I forgot to put parentheses. Man, the very problem that I accuse my students of doing all the time, I am doing it. 3. Okay. And I think I'm still doing it wrong. Good grief, Charlie Brown. I'm sorry, hold on one moment. Let me take a look. I want to make sure that I give you guys the right answers. I don't want to give a wrong answer and then have to go back and change that. Okay, so it's opening up. Look at it. Okay. I did something wrong. I did with my calculator. So clever. 1.99 exponent negative 1. Oh, I forgot to square it. Oh. You know, it's kind of a bummer about the Hangout stuff is that you guys are probably on the other end going, Mr. Warner, you gotta square it. And I, of course, can't hear you. What a bummer. Okay. Once I do that, I think that it will all work out. Why, yes, it does. Okay, so the answer ends up being 4.55 times 10 to the negative 1 molarity. And the key says 4.55 times 10 to the negative 10th. And I think that when he writing this key, he put a typo in there, but I think it's just in the answer key. I think it should have been 10 to the negative 1. So yeah, that one was way off. I thought I talked about it in class, but we only talked about it to a few groups. So sorry about that. But that answers that question. Yay. Okay. Let's answer another question. I'm going to, you know what? Oh, there we go. Since I'm on 13A and Ali had number 1, 5, and 6A. So I've already done number 1. Why don't I go ahead and do 5 and 6A on that same document? All right, so let's take a look at those questions real quick. 5 and 6A. All right, so number 5 says, calculate the equilibrium amounts of each substance in the reaction below if an initial amount of 0.4 moles of carbon monoxide are brought together with an initial amount of 2.2 moles of chloride, a gas, they're both gases, and then equilibrium is established at 900 Kelvin. Kc at this temperature is 0.80. So this is good because this kind of fits in with some stuff that I really want to talk about, is identifying the concentration of things at equilibrium when given the K. And 6A, oh, I like it. Oh, yes. So they have a percent. That's really good. You know what? I'll just come back to that one. So let's just do number 5 right now. I'm really glad you guys are asking these questions. This fits perfectly with what I was hoping you would be asking. All right. So let's open up a new page here. And we're doing number 5. So number 5, worksheet 13A. All right, our equation is, we have some sort of carbon chloride, I don't even know what to call that one, what that gas is called. I don't know. And it is in equilibrium with it decomposed into carbon monoxide gas and chloride gas. Interestingly enough, all the coefficients are 1, which should make that a little bit easier. Now, you have some initial amounts and you have some final, well, you don't have any final amounts, but you know what the K is. Kc is equal to 0.80. So what we need to do is create our ice table. And they're all gases, so they're all going to be a part of this. And so we originally have an amount of 0.4 moles there and 2.2 moles there. And there's 0 of that. We'll call it the reactant gas, COCl2. And so we know that when this goes, it's going to go the direction where there is nothing. Like wherever the 0 is, it's going there. So we add a plus x there. Everything is 1 as a coefficient, so we're not going to be doing any coefficients on our x's, which means we're going to lose some amount from the 0.4 and we're going to lose some amount from the 2.2. So we're left with x, positive x for the COCl2. We have 0.4 minus x for our CO and 2.2 minus x for our Cl2. Now we know that our K, Kc, is going to be equal to our products, carbon monoxide and chloride gas, divided by our reactant, which is Cl2, which means that 0.80 is going to be equal to 0.4 minus x times 2.2 minus x divided by x. So what we have here is we're going to be doing some, I can't remember what it's called, factoring out our the FOIL method to distribute. I don't remember all the terms, but I would say this. So you're going to be doing algebra. This is algebra. Granted, there's a lot of it, but there's algebra, okay? So you're going to multiply both sides by x. I mean, I don't want to have to write out all these steps. You guys should be remembering this. So these x's, and I'm going to multiply both sides by x. So these x's go way over here, and you're left with 0.80x equals 0.4 minus x times 2.2 minus x. Then you're going to FOIL, right? That's all I know. I don't know what you guys call it. First, outer, inner, last. So the first, 0.4 times 2.2. So I'm going to use a calculator because I just don't want to think about it. 2.4 times 2.2. And so I'm going to get 0.88. Now I do the outers. So 0.4 times negative x, that's going to give me negative 0.4x. Then the inner, negative x times 2.2. So it's going to be minus 2.2x. And then that's going to be, then last, minus x times minus x equals x squared, okay? And so we're gonna, and that's 0.80x. So then we just have to rearrange this a little bit to make it a little bit easier, because I'm all about easier, I gotta be honest with you. I'm just gonna move it all over on the other side to make it equal to 0. And make a lot of these things positive, right? So we're gonna, because you're adding, like you add these together, and really that's negative 2.6x. This is minus x squared, and that's a positive there. So what I'm gonna do is this is gonna become, when I add these together, just so that I don't confuse you, minus 2. Okay, so now I'm gonna add, right, 2.6x and add x squared, and I'm gonna subtract 0.88, and then I'm gonna do the same thing to the other side. So I'm gonna end up with x squared plus, and then we've got the 2.6 plus the 0.8, 3.4x minus 0.88 equals 0. Okay, now you have to consider the x, because the k is equal to 0.8, which is too large, so you can't do negligible. So if you want to do this by hand, which you are welcome to do, you have to do the quadratic formula. So feel free to do that. Otherwise, you can use the solver on your calculator, or you can just, I think you can do this stuff online. I think they have quadratic solvers online. Let me look that up. Quadratic solver. Oh, look at that. How about that? So, all right, so if I plug these things in, let's see what I come up with. Again, I don't know what the answer is right offhand. 3.4 for my B, and my C is negative 0.88. And when I do that, I get negative 3.6416 and positive 0.24. And I would say that, and you can, again, you can do the points, like when you can graph it and grab the points of the line, and this becomes really easy, because then the negative cannot be the concentration. You cannot have a negative concentration. So based upon the solver, I would say that x is equal to 0.24, which is equal to, we're looking for the final concentrations of all of them. So that means that the concentration of COCl2, right, that's equal to 0.24. And if I want to find the concentration of CO, I have to take, it's equal to 0.4 minus 0.24. So that's, what is that, 1.6? No, not 1.6, 0.16. 0.16 molarity. And this is molarity too, I keep forgetting to add that in. And then you get where this is headed. The chloride is 2.2 minus 0.24. So I'm just kind of winging this. If you're losing 2, it goes down to 2. Or you're losing 0.2, it goes straight down to 2.0. If you lose another 0.04, that's, I think it's 0.96 molarity. And I should look and see if there's a key nearby. 13A, number 5. 1.92, 0.12, and 0.28. His answers were different than my answers. I'm not sure why that is. It's very possible that I did something wrong in those calculations. It has been a long time, but just trying to think. Let me go back and take a look at the original problem. It's 0.4, 2.2, 0.4 minus x, 2.2 minus x. I wish you guys could talk to me and tell me if I did some of the math wrong. Would be really helpful. Let me take a look. Well, unfortunately, I'm not sure where my mistake is, because that is absolutely what I'm getting. Oops, minimize the wrong sheet. Where's my, now I can't find my, my sheet. Okay. I was off by, according to his thing, I was off by another 0.04. So he was saying it was 0.28 was the concentration of the COCl2. And I wish I had a solutions manual to see this. Let's see. Well, I would say this. If you guys know, if you guys see where the mistake is, great. I don't see where that mistake is. Honestly, I believe that I solved it correctly. Products over reactants, no different coefficients. Using the FOIL method, maybe I did my math wrong. 0.4 times 2.2, 0.88. Maybe I added them wrong. Maybe I did that. So 0.4 plus 2.2 plus 8, 3.4. I don't know. I don't see it. Okay, well, I'm sorry. I obviously my answers do not agree with his answers. So if you guys understand where the mistake is, great. If not, I am going to claim typo on his fault. No, honestly, it's probably something I'm doing wrong. I don't know what it is though. But that's basically how you would solve that. You will not have to do, here's the cool thing. You won't have to do the quadratic on the test. You won't have to do the quadratic on my test. Normally you have to do the quadratic on the AP exam. They do not do the quadratic. So I hope that puts your mind at ease a little bit more about that one. Okay, so we're gonna move on to 6A because that's fun. Okay, 6A. All right, so this is the one where we had 1 mole of N2, 3 moles of H2. So it's that Haber process again, and only 50% of the N2 that was present originally remains. Oh, they're not even giving you the stoichiometry. They're just staying straight up. It's 1 mole and 3 moles. Okay. This is good. I like this. It looks like it's a pretty straightforward problem. I'm hoping that it really will be straightforward. New page. Okay. So let's try it. Number 6A. Worksheet 13A. All right, so we have the problem N2, or the equation, plus 3H2 is in equilibrium with 2NH3. We're calculating K for this. And so we're going to have to do an ice table. K is one we don't know. And we start with 1.00 and 3.00. Now, on the test, there very well could be a question where they do this, but they say that while they say that 50% remains. So what they're saying is that you're subtracting 1.00 times 0.5. Okay? Because that was the N2. So you and I can do that in our heads, but if a problem is presented to you where you can't do it in your head, then you'll show a little calculation over here, 1.00 times 0.50, whatever, you can see they're all 3 sig figs, is equal to 0.50 moles. Okay, so you know that you're subtracting 0.5. And that is the X, right? Because right here, that is that, but it's also, for N2, it's minus X. And then this would be minus 3X, because this is 0, and this is going to be plus 2X, okay? So you're going to have 3 times 0.5, which should be, I believe it's 1.5. So, you're going to be at equilibrium at 0.5. This is going to be subtracting 1.5, because that's 3X. So that's going to leave you with 1.5, because 3 minus 1.5, that's the change. And on this side, it would be 2 times X, and the X is 0.5. So that's, we'll just say 2 times 0.5, which is equal to 1. So you're going to end with 1.0. And Kc is equal to the products, which in this case is NH3, products of reactants, NH3 squared over N2 times H2 cubed, which is equal to NH3, which is 1 squared, over N2, which is 0.5, and H2, which is 1.5 cubed. K is equal to, when I do this, 1 divided by 0.5, well, I don't know why I did, that's 2. Divided by, I don't know this, 1.5 to the third. Okay, so according to my calculations, K is equal to 0.59. Oh, it's 3 sig figs, 592. Nope, 593, because it's 5925. Okay, and so I take a quick look at the key, and for number 6A, 0.593. Perfect, okay. So that's how I solved 6A. So that's 1, 5, and 6A. 1 was a typo, 5 was, I sure hope it was a typo, otherwise I blew it, and you'll have to ask me later. Or you'll have to correct me, and I'll have to talk to the class about it. And that was 6A. All right, so the next one's ARIA. Multiple choice number 7, 8, 9 on the practice test. So let's go back. Where did I put it? There we go. Okay. So I'm going to go ahead and share the test with you. All right, we're now going to do number 7, 8, and 9 on the practice test. And we might as well just take them one at a time. I think that's easiest. Okay, oh, we have a big problem. Oh, love it. Okay, so this is where they give you a problem and ask you to answer multiple questions about that one problem. This is very, very common on the AP exam now. Used to happen only once in a while, but now it's, they try to group almost all of the questions with a narrative or a section of information first. Sorry, I just need a little something to drink. Okay, so they give you an equation where it's hydrogen gas plus carbon sulfide gas. It gives you methane gas plus hydrogen sulfide gas. Wow, that's a lot of nasty gases. The system reaches equilibrium. A mixture of 4 moles, 0.5 moles, 2 moles is placed in a 2-liter vessel when equilibrium is achieved. The concentration of CH4 has become 0.5. The 5 questions below. Okay. It says 5. Wait, 7, 8, 9, 10. I think I skipped or I cut one out and forgot to change that part. All right. Well, let's go and switch to the bamboo tablet. They want to know what is the concentration in moles per liter. The molarity basically is what they're asking of H2 at equilibrium. So bamboo tablet. Okay. We are going to do, I'm going to switch to a new page, number 7. Practice test. Okay. And so our equation is 4H2 plus CS2 in equilibrium, CH4 plus 2H2S. All right. And let me just double check again because I got to put all those numbers in. All right. So we have, and we're going to do an ice table, 4 point. Oh, you know what I'm going to do? I was looking ahead because we have volume equals 2.0 liters. So basically, if we have 4 point, oh my goodness, my writing. Okay, so if we're looking, for example, the H2 is equal to 4.00 moles in 2.0 liters, which is equal to 2.0 molarity. As an example. So you need to make sure that you are keeping track of this. They want the answer in molarity, so you need to use molarity in your concentration. It would just be easier. Obviously, you can change it at the end if you want to do the whole thing with moles and then come in and divide your moles by liters. The problem is then they give you the concentration of one, like the methane, the CH4, they give it to you in molarity, whereas they give everything else in moles. Totally tricky, not fair. It's the way it is though. Got to pay attention to what they're saying. So the initial concentration of the H2 is 2.0 molarity. The concentration of the, I'll make sure of, 2.00 moles of CS2. Okay. So the CS2 has 2.00 moles divided by 2.00 gives you 1.00. You know what? Since we're doing all this in concentration now, I've said it, you guys got it. I'm going to go ahead and just take the units off because the whole table is in molarity. So 2.00 for the hydrogen gas, 1.00 for the carbon sulfide. They give us 2.00 moles of hydrogen sulfide divided by 2 gives you 1.00 1.00 as that molarity. And they did not give you any methane. It's not listed. If it's not listed, if it's not even mentioned, you can assume it to be 0. Okay, you can assume it to be 0. If they gave you all those numbers and they said, and some amount of methane, well, then that's your X. Or that's one of your X's, I suppose. They could get really complicated really fast. Now, at equilibrium, they said that the answer was 0.5 molarity. The coefficient on methane is 1, which means that you have plus X there. And plus X now has to be equal to 0.50 molarity. Okay. I said I wasn't going to do concentration. I want to be consistent. We're only down to 2 sig figs now. So this was minus X, or I'm sorry, this was plus X, because you're going to the side with the 0. That had 0. Yes, you have 1 molarity here, 1 molarity here, 2 molarity here, except the problem is you can't go the other direction. It's just impossible. When you have 0 for CH4, no carbon can be used to make the carbon sulfide. So it has to go to the right. And I'm going to go ahead and change this. I'm just going to show it. So that means that it's going this direction, right? Because there's no carbon. So you've got to make carbon, okay? So if it's plus X there, this is plus 2X. Fascinating. So that means it's going to be, you're going to get another 1 out of that. It's going to be 2.00. This one is a minus, there's a coefficient of 1 minus X, which minus 0.5 is going to give you 0.50 minus 4X. Oh my goodness. You've got to be kidding me. That's impossible. How is that possible? Did I make sure of? Oh, I am tired. I'm very sorry, you guys. I am not thinking straight. I was at a conference all day for the last 2 days, and I did not get a lot of sleep last night because I was preparing to present. So I totally blew this one. I was reading it wrong. Okay. Let me delete some of this stuff. Let me start over. Okay. So frustrating. So frustrating. I'm sure it's very frustrating for you guys too that are watching. You've probably seen them snake happening. It's like a train wreck and you guys can't stop it because you can't say anything because it's just the questions. I'm not even looking at the questions. Let's try this again. We had, it's all in 2 liters, so at least that part's right. So that means you have 2.00 molarity of the H2. Okay. Then for the CS2, we had 2 moles. So 2 divided by 2 is 1.00. For the CH4, you actually had 0.5 divided by 2, which leaves at 0.25. Yeah, because now that the 0.5 is divided by 2, which is basically like 1/4. And the H2S is 2 divided by 2, so that's 1.00. Okay. So they give you the equilibrium as 0.50. So at least we had it going the right way. It's still going to the right because the 0.25 to get to the 0.5 is going to have to add some amount to get there, okay? Easy enough to figure out. X has to be equal to 0.25, right? Because it's 0.25 plus X equals 0.50. All right, so we got that. So if that's plus X and X equals 0.25, that means this is plus 2X, which means my answer is 1.50. This would be minus X, which means this is 0.75. And this would be minus 4X, and 4.25, 4 times 0.25 is 1. So at equilibrium, hydrogen is 1.00. And the question for number 7 was, what is, H2 concentration at equilibrium? It's equal to 1.00 molarity, which is that moles per liter. Good grief, Charlie Brown. I'm sorry. Waste of a few minutes. That's okay, we'll get it back now. I'll run long on this because I want to answer all these questions. Even if you've answered a question, you need to go. We'll fix it. I'll do it. All right, let's share the document again. Okay, now we're on to 8. I think part of my problem is I made that really big and I didn't pay attention to how big I made it. So I didn't see the whole question. Totally did it to myself. Okay, 8. What is the change in the number of moles of H2S present as the system moves from its original state to the equilibrium described? Change in number of moles of H2S. Well, let's take a look. H2S. H2S, right here. The change in moles was plus 2x, so it was a times 0.25 times 2, which is 0.50. So let's see what answer 0.50 is. 0.50 is C. That is the right answer, C. All right, number 9. What is the number of moles of CS2 at equilibrium? This is, at this point, you guys should be killing this. Oh, goodness gracious. At equilibrium, right? What's the moles of CS2 at equilibrium? Looks like it's 0.75. Wait, minus 0.75. All right. I hope I'm doing the right sheet. Because, oh well. All right. C, 1.50. CS2? That is not right. There's a mistake. We're going to change. We're going to change 1.50 to 0.75. Yay, that's the right answer. Okay. Yay for us. So now C's the right answer. I'll have to change that. I'll have to make those edits. That doesn't feel right. I don't remember doing this now. I wonder if I'm doing the wrong test to you guys. Totally would be like me. That would totally be like me. In fact, you know what I'm going to do? I'm going to do 7, 8, 9 on the other practice test because I bet this is not the test you guys wanted. Okay. Okay, let's take a look. 7, 8, and 9. Oh, those are tough ones. Oh, and one of them, number 8, I said you could use a calculator. I can see that. So why don't I just go ahead and do 7, 8, 9 for you? You guys just like, I'm not going to go back and forth on this. I need to pick this up a little bit. Since 9:01 now, I'm having quite the marathon one tonight. I can just feel it. Totally my fault, the reason it's a marathon, so that's okay. Let's do it. All right. 7, 8, 9. Where did I put it? There it is. Okay. So this is, we'll call this practice test original. I'm pretty sure this is the original. I remember spending some time on this one. So which expression best describes the relationship between solubility product KSP and the solubility S of Mg F2. So solubility product, just so you can totally understand all the jargon, solubility product is the same thing as KSP. And molar solubility is the same thing as if they just said solubility. Okay, so you have MgF2, which means that as a solid, it is in equilibrium and breaking down into Mg2 plus 2 Fe minus. And these are both aqueous, of course. You can't really read that, but it's supposed to be aqueous. So that means that your KSP for this is equal to the concentration of the Mg2 plus times the concentration of the F minus squared. Okay, and this is going to be 2. If this is X, this is 2X. And actually, we represent it with an S. So that's S times 2S squared, which means that it's S times 4S squared. So it means KSP is equal to 4S cubed. And let's see. Yes, that's D. Excellent. All right, number 8. So you can use a calculator for number 8. So this one's looking for molar solubility. So this one is looking for the S. Molar solubility, which is basically S. And it's in, wow, Fe2, S3. That's an ugly looking one. And they give you the K, SP, as being equal to 1.4 times 10 to the negative 88th. That is a huge number. Okay, so Fe2, S3 dissociates into 2 of the Fe3 pluses plus 3 of the S2 minuses. Good Lord. KSP is equal to, what did you say, the concentration of Fe3 plus squared times the concentration of S2 minus cubed. So KSP is equal to S squared, oh no, I'm sorry, 2S squared times 3S cubed. So if I take that over here, and K is equal to 1.4. 1.4 times 10 to the negative 88th is equal to, and this is 4S squared and 9S cubed. So we're gonna have that equal to 36S to the 5th. Wow. That's so much fun. So 1.4 second function e negative 88. So that's divided by 36. Enter. And we're going to put it to the 1/5 power because it's -5. And on my calculator, I get 1.3 times 10 to the negative 18th. Yikes. And I look at the answers, and D is the only one that has a 10 to the negative 18th. The other ones are too crazy. So 1.1 times 10 to the negative 18th. That is the correct answer. All right, let's do number 9. Oh boy. What is the concentration of chromate in saturated solution of lead chromate, KSP, of 9 times 10 to the negative 14? The concentration basically is the same thing as molar solubility. Concentration equals S equals molar solubility. It's all the same thing. Isn't that cool? Soluble. I'm still having a hard time spelling solubility, whatever. All right. And they give us the KSP as being equal to 9.0 times 10 to the negative 14th. And I said this was a no calculator problem. So we have PbCrO4 in equilibrium dissolving into its ions. Pb 2 plus CrO4 2 minus. So the KSP is equal to the concentration of the Pb2 plus. No coefficient, CrO4, 2 minus. In brackets, I'm doing that too fast. So that means it's 9.0 times 10 to the negative 14th. It's equal to S times S. So we've got S squared is equal to 9.0 times 10 to the negative 14th. So I'm going to square root S, and I have to square root the other side. So S ends up being 3.0 times, because it's square root of the 9. When you square root an exponent, it's like dividing it in half, so 10 to the negative 7th. So 3.0 times 10 to the negative 7th. And that's A. Yay for us. We just solved that one. So we did 7, 8, 9 on both tests, and hopefully you got a question on one of them. Done. My voice is cracking. All right, Joanne, how do we know if we need to use an ice table? Great question, Joanne. Ice table. Okay. So the truth is, you can always use an ice table. Okay. So whether it's KC, KP, KSP, later we're going to learn about KA, we're going to learn about KB. You could always use an ice table. I mean, even with the solubility, right? I mean, if we're talking about Pb, CrO4, which is a solid, in equilibrium, and going down to Pb 2 plus, which is aqueous, by the way. CrO4 2 minus, also aqueous. And we do an ice table. Solids do not count, so we can get rid of them. And we know that this is 0 and this is 0 because in the process of dissolving, you don't have any ions and it goes that direction. You are going to add an X. You're going to add an X. And we're going to say that X is actually equal to S later on. So this is X and this is X. So what you have is when you have your KSP is equal to, Pb 2 plus times CrO4, because those are the products divided by the concentration of the reactant. Pb CrO4 concentration, but it's a solid, so that goes away. And then, so basically KSP is equal to X times X. However, it's KSP, so we use S. So KSP is equal to S times S. So you can use an ice table. You know where it's going to go. So that's why I didn't use an ice table. If it's KSP, you know where it's going to go, so you don't have to do it if you don't want to. But you absolutely, if you're not feeling confident, use an ice table. Okay. That problem 13a in equilibrium, I think by saying equilibrium, he's just being tricky. If you have to do a calculation with K, excuse me. So if you have to do a calculation with K, you're probably going to have an ice table. At least for this unit of calculation, I am so irritated. This is just looking horrible. Calculation is involved and equilibrium is mentioned. I can't spell. I cannot spell anything. Mento. What is that? Is mentioned. Make a nice table. Now, that's my, hey, if you're not sure, like when in doubt, make a nice table. You're not always going to be asked for a nice table. I mean, if it says equilibrium, and you've got to learn to read the questions and critically think about them. But, you know, to be safe, make a nice table. Graders, AP readers are not going to complain about the fact that you did a nice table. It's not going to happen. They're glad. I mean, you're demonstrating knowledge of chemistry. And I can't tell you how many conversations I had last year, and some of them are like, readers get frustrated because they love it when a student shows a comprehension, like an understanding in chemistry, and maybe they didn't get the points, but it's there. Like teachers, these are college professors, these are high school AP teachers. They love that. They love that. They love that. They're going to really try hard to give you points if you're doing that sort of stuff. So if you can, make a nice table. That's what I would say about that one. All right. So we're done with that question now too. I had several questions. What is K versus Q? I'll just talk about it real quick. K versus Q. Q is this not at equilibrium. K is equilibrium. K is equilibrium. Q, conditions not at equilibrium. And so when you're not at equilibrium, you want to know which way you're going to have to go to get to equilibrium. So I haven't seen it on a test recently, an AP exam. It's not on my exam, but there are problems. It exists. Like watch College Board put one on the test this year. But sometimes you have to calculate Q. They'll say these are the concentrations not at equilibrium. And they'll say which way will it go to get back to equilibrium? Will it shift left, shift right? And so you calculate Q, and they say, and they give you K. And remember that I have a K and a Q here. You have to set the alligator mouth. So you do your calculation, you find Q, and you're like, oh, Q is bigger than K. Well, then you know what? It's going to favor reactants. Oh, I see your post. Joanne, you're welcome. You said thanks, you're welcome. So K is less than Q, so it's going to favor the reactants. Okay. If you do the calculation and Q ends up being less than K, then it's going to go to the right. Okay, it's going to go whatever way the arrow points. And that one's going to favor products. Okay. So hopefully that that helps you a little bit when you're doing that. If you have to compare K and Q, put the K first, put the alligator up there, and you'll know which way the arrow goes. All right, so there we go. Okay, so there was a K1, how to solve, and you guys already did that one, how to solve for K, how to solve for concentration in a nice table. We did that already too. Quadratic formula, I'm not going to have to do. Remember that if K is less than 1.0 times 10 to the negative fourth, then X is negligible. So whatever the number is, minus X or plus X is equal to that number. So 0.05 minus X is equal to 0.05. Now it's kind of close. You probably have some other concentrations a bit larger, but that's pretty much it. Because you're going to get concentrations like one, or you're going to get K's like 1 times 10 to the negative 10th, 1 times 10 to the negative 18th. And that's how you're going to know. So good to know. Don't forget that. All right. How to solve for K in a nice table. We did that. And, oh, how to solve. Wow, you guys did a great job. I mean, they're all back in this video. So if you're still watching this, or if you're watching this later and you've skipped to this point, go back. There are questions in the free response where you had to do that, answer some of those questions. So I should have selected some of that too. That would have helped. Anyways, that's how you solve all of that. It is now 9:17. So this is one of my longer ones. And I brought it on myself. My apologies. So hopefully you guys get prepared. Please come in and see me tomorrow if you have questions. If something didn't get answered, if you found a mistake in what I was doing, I'd love to hear it. I really would. I really want to make sure that I do this right. Get some rest the next couple nights. I know I will be, or I'm going to try to be. And I will hopefully see you guys tomorrow or on Tuesday morning. All right. Take care. Bye.